Welcome back to the video session of ground improvement techniques. In this session we are going to see what is hydraulic modification and what are the different methods used in hydraulic modification. So in hydraulic modification we are trying to reduce the groundwater level and excavate the water present in the ground. So free poured water is forced out via pores by drains or wells. In coarse grain soils, we achieve this by lowering the groundwater level through pumping from boreholes or open sumps or ditches. In fine grain soils, we try to take off this water by long-term application of external loads or electrical forces is also sometimes required, and we call this technique as electroosmosis or electrokinetic dewatering. So generally there are many methods in which hydraulic modification is done nowadays, but the traditional dewatering techniques involves three types of methods. First one is open sumps and ditches, the second one is gravity flow wells, and the third one is vacuum dewatering wells. In open sumps and ditches, we try to excavate some part of the land and allow for some days or some time such that water comes and settles down in these open sumps and ditches, and we try to pump out them. Next is gravity flow wells, in which it is also a well type system in which we bore some wells into the ground and water flows into this well due to the gravity, and we try to pump out this water with the help of some centrifugal pumps. Whereas the third one is vacuum dewatering wells. The first two methods are generally suited for the coarse grain soils, whereas we try to use this vacuum dewatering well systems for the fine grain soils. So generally, if at all in fine sands or silts with permeabilities of 10 power minus 4 to 10 power minus 6 meters per second, where water does not flow freely under the influence of gravity due to capillary tension, we use vacuum dewatering systems. So to dewater and stabilize these soils, a vacuum may be applied to seal off filter section in the well. So seepage into this well is thus increased due to the influence of atmospheric pressure. Water inflow is generally low, and hence these wells require only intermittent pumping out. So intermittent pumping out means pumping out of water at stages. So we don't pump out the water continuously because the inflow of the water will be very low in such kind of wells. So vacuum action is also present in the well point systems, which use a combined vacuum and a centrifugal pump. So care should be taken that all the connections in the pump system are airtight, because we are going to introduce a vacuum system in this well system. So to be effective, vacuum wells are spaced closely of 1 to 2.5 meters apart, and the distance between rows of these wells should not be more than 15 to 20 meters. Submersible pumps in combination with vacuum pumps could provide dewatering to greater depth. Horizontal systems are also conceivable. So if at all we want to find out, or if at all we want to find what is the capacity of a well or how much water we are going to dewater it, we should first know about the pore pressure, permeability of the soil, and some physical properties of the soil. So before going into a detailed study of design of the well systems, and also let us know some basics like how do you find out the permeability of a soil. So there are many different methods in which you can find out the permeability of a soil. You can estimate the permeability from particle size. We can estimate the permeability from the laboratory procedures, and we can even do some field test procedures. But in this session I am going to discuss only about the laboratory procedures. So we have two types of laboratory procedures. One is constant head test and the other one is variable or falling head test. So let us see what is a constant head test. We have an upper reservoir and we have a lower reservoir level. So let us assume that this is a specimen with a length of dx and an area A. So let us see that what is constant head test. Water flows from the upper reservoir to a cylindrical soil sample of length dx and a cross section area A to the lower reservoir for a given difference of dH. in the water level between the constant head reservoir, and the flow of water is measured and we call as discharge Q. So now the coefficient of permeability K is calculated from the Darcy's law as Q by A into dx by dH. Here you can see that this dH, or the given difference between the upper reservoir level and the lower reservoir level, is maintained constant throughout the experiment. Hence we call it as constant head test. Now let us see what is falling head test or variable head test. So in this also we will be having the same soil sample of area A, and water drains from a standpipe. So this is a standpipe. Okay, so water drains from a standpipe through the soil specimen to the constant level reservoir, and let us assume at time t1 the head in the standpipe is h1, and at time t2 the head in the standpipe is h2. So it has fallen to h2. So the cross-sectional area of the standpipe is A, and this is a standpipe, and the area of this standpipe is assumed as small a, and that of the specimen is assumed as capital A, and the length of the specimen is taken as dx. The coefficient of permeability is found to be A into dx by A into t2 minus t1 to the natural logarithm of h1 by h2. So this is the falling head test. Here you can observe that the difference between the upper reservoir level and the lower reservoir level is not maintained constant, and hence we call it as variable head test or falling head test. We even have some field tests to find out the permeability. One of the major field tests is pumping out test with observation holes. In such kind of test, we have an installation of full size pumping well plus at least 2 additional bore holes where the piezometric level can be measured, and we have a different formulae to find out the permeability for unconfined flow and for the confined flow. Now let us see about the design considerations of dewatering systems, and what are the considerations you should take for each and individual component of dewatering system. So there are three major criteria to be considered in design of dewatering systems. First one is design of filter criteria and well screens. Next one is the individual well capacity, estimation of individual well capacity, and the determination of well depth, diameter and spacing. So what is design of filter criteria and design of well screens? So let us see it. So in open drainage situations, it is desirable that water does not exit on slopes. So in order to prevent slumping, we will construct a sloping filter in such conditions. Even there is a scientist who has provided a design charts that show us the ratio of K, or this permeability of filter to the permeability of soil ratio as a function of slope S. So if at all we find out the permeability of soil from the permeability of soil from the laboratory procedures or from the field test, and as we know the permeability of filter, because it will be obviously a commercial filter or a man-made filter, will be knowing the permeability of it. So we can find out this ratio, and from the design chart, based on this ratio, you can find out at what slope should be the filter installed. So in traditional way of preventing the migration of fine soil particles into ditches and sumps is to construct one or several filter layers, usually consisting of sand with grain size chosen according to the filter criteria. So this criteria ensures adequate flow through the filter zone, prevention of piping and sufficient uniformity of the material. So the criteria is expressed in terms of grain size indicators, that is D15, D50 and D85, and if at all we are going for temporary installations or temporary wells, it may consist of a perforated casing surrounded by sand or gravel pack, but whereas more permanent installations are likely to be fitted with the commercial well screens. These well screens are made of corrosion resistant metal and have a V-shaped slot openings that widen inwardly to prevent the clogging and to allow the maximum discharge into the filter. A properly chosen well screen will give the well a maximum specific capacity measured in liters per second per meter of drawdown. I repeat, a properly chosen well screen will give the well a maximum specific capacity measured in liters per second per meter of drawdown. So next we will see individual capacity of well. So before we go for the design of total well system, it is very much essential and necessary that we should find out an individual capacity of the well or capacity of each single well. So the preliminary design of dewatering system depends upon total quantity of water to be pumped out for a circular excavation. So in order to estimate the required number of wells of a given size, knowledge of the capacity of an individual well is required. So for an individual well of radius smaller, the discharge quantity is found to be this, that is 2 pi r HWK into I. That is, r is the radius of the well and I is the average entry gradient. So according to the empirical findings, the entry gradient should not exceed 1 by 15 into root k, where k is the permeability in meters per second. So hence if at all we substitute this formula, the value of maximum entry gradient in this discharge of an individual well, we can find out the capacity of an maximum capacity of a well, that is 2 pi r h naught into root of k by 15. And for an open well, the discharge is found to be this. So a straight line is obtained when a graph is plotted between Qi max and H naught. So if at all we plot a graph between Qi, that is discharge of individual well, and the maximum discharge, the limit of an discharge of individual well with respect to the H naught or H, we obtain two graphs, that is one is a straight line, that is Qi max versus H naught, and the second one is Qi versus H naught, which have a parabolic representation or a parabolic variation, and these two graphs get intersect at a point called as A. Point A corresponds to desired minimum water level in the well, H naught minimum, and optimum discharge. So this Q optimum representing the individual well capacity. If Q is further increased, maximum entry gradient according to the formula is exceeded and the well may be pumped out dry. So if at all we are going to excavate water or dewater with the help of a well, we should not pump out more water than this point. We should not pump out the discharge which we find out from this point, because if it will be pump out more water, there's a chance that the well may get dried. So care should be taken while calculating the individual capacity of a well. Next one is well diameter, depth and spacing. So we have shallow installations using surface pumps with a maximum suction head of 8 meters. Well screens may extend the installation to a depth of 10 to 12 meters. So there is also a course from different scientists that the distance between the adjacent wells should not be less than 3 to 4 meters for a 150 mm diameter well and less than 5 to 6 meters for 300 to 350 mm diameter wells. So this is the standard design approach or the basic things considerations considered when we go for a basic design of dewatering system. In the next session, let us see what is an exactly standard design approach of these wells or the dewatering systems. Thank you.